So, hello everyone. Welcome to the second session of our computational social science seminar this semester. And I'm humble. I'm one of the organizers of this event. And today we are very excited to have Junming Huang visiting us from Princeton University. Junming right now is an associate research scientist at Princeton University, and he has a very interesting and diverse research background. He was a physicist by training during his bachelor at Tsinghua University, and he later obtained his PhD in computer science before traveling to the US. In the US, he has been working as postdocs with the Barabasi group at Northeastern University and later as a research scientist at Princeton to understand some of the most interesting social questions with computational methods, including that how do we quantify success and how do we understand team collaboration and innovation with computational method, and in particular related to today's topic, that how do we understand gender inequality in science. So without further ado, I will give the floor to Junming.
Thank you. So I want to first apologize that I might look a little bit weak today because I have a cold yesterday. This one is a little bit more colder than I anticipated. So thank you, Hongbo, and thank you all the organizers. It's quite an honor to join this workshop of computational social science. And I'm happy to present our finding in Science of Science recently. So to continue with the introduction, Junming, I'm an associate research scientist in Princeton. I'm currently working on a wide range of topics on computational social science, like science of science, public opinion, social network analysis, natural language processing, and a little bit causal influence. So my background is a mix of physics and computer science, and currently I'm working with a couple of sociologists. So that's why I enjoy use large-scale empirical data and deep models to understand human behaviors. Today I will share one of our studies on analyzing gender inequality in scientific careers, thanks to my collaborators, Alex, Roberta, and Lance Torbush. This paper was published in PNAS in 2020. So let's start with a little bit of background in in science of science. So science itself is a complex phenomenon that millions of people, they are involved in scientific discoveries. So with very heterogeneous behaviors and outcomes. So how are the scientists grouped? How do they organize themselves into hierarchy? And how are scientists and papers linked? How do they get recognized in the community and out of the community? If we consider science as a dynamic process on a network, we make a quantitative understanding of scientific activities. That's why we're working on science of science with big data analysis. I start with introducing a couple of representative studies as examples of using bibliometric data for the science of science study. So this is the second figure on the upper row is a 2014 PNAS paper when my previous colleague Shen developed a collective method to quantitatively measure the credit allocated between co-authors. This is a long-term question in the science of science study, that how do we know which author contributes more than another author when all of them are listed as co-authors on the paper? So people usually believe that author orders tells the rank of importance, but that's not true, because in some disciplines, like in math, authors are ordered by their alphabet, by their names, not by their contribution or importance. So the proposed algorithm uses the citation network. They just collect for, say, we have a paper, like Hongbo and I, we have co-author paper, and we'll find all the papers citing this paper, and say how many papers those papers are citing, and count how many papers I and Hongbo appear in those papers. So when we are calculating how many times I appear in co-cited papers, I'm actually measuring how important I am in this community. How do I continue my effort into this topic? And that helps us to recognize co-authors' credit in a co-author paper. This is a very interesting result that they find that they use a Nobel Prize to validate whether this proposed algorithm works. So this is each vertical line is a Nobel Prize with more than one authors. So say a paper with 8 authors has won a Nobel Prize, and only 3 of them, only 3 of the authors finally won the Nobel Prize. And which 3 of them? The red dots are the algorithm correctly predict which 3 of them won the Nobel Prize, and black dots are incorrect predictions. I can say the algorithm is quite accurate. It predicts like 75% or 80% of the authors that are finally recognized by the Nobel Prize community. So the second, the right figure on the upper row is a citation network. I use citation network to map out network science. So I identified about 40,000 of network science papers and group the top 500 top cited ones to show the topological structure of those papers. This is a co-citing network. So nodes are papers and the colors represent their fields. So we want to use this little structure to show how the papers are organized into a hierarchy. You may find the network science has a very dense core of blue and the green papers, which are physics and math. And it has a couple of branches to life science, to computer science, and social science. And this one is one of my favorite papers. This by Linfei in 2019. Now, Linfei addressed a very a long-term question: how do we know the novelty of a paper? How do we know whether a paper is disruptive? So Linfei found this is a very elegant algorithm that he found how many triangles are there in the citation network, measures how novelty your paper is. If all the papers that are citing your paper, they also cite your references, that means your paper is just one of a lot of papers that are, but if all the citing papers that do not cite your reference, that gives a hint that your paper might be new. It might bring some new information from another community to this community, and that measures the novelty of your paper. And this one is a 2013 science paper by Junming Huang. He tackled what factors could determine a paper's citations. In this figure, every curve is one paper, and it shows how many citations this paper gets in every year. So it looks very messy and random, but they prove that only 3 parameters can be used or sufficient to describe this long-term dynamic process, including a paper's quality and the log normal aging factor. And the last one is a 2015 CSS paper that my colleague Roberta Senator, they found a way to automatically detect physics papers, and then they analyze how the boundary of physics papers evolved in the past 100 years. And they also found the evolving connection pattern between physics subfields. They use a lab spread algorithm to detect the boundary of physics, and they found some subfields of physics were becoming more isolated now with less citation links to and from those subfields. So those are a couple of examples of recent progress on the science of science topic. And what we're talking about today is the gender inequality. So in many aspects of scientific activities, female scientists are underrepresented. For example, in the history of Nobel Prize, there are a total of 851 individuals have won Nobel Prize in natural sciences, physics, chemistry, and medicine. And only a small portion of them, 84 of them, are women. As reported by US National Institute of Health, the average size of women's funds has consistently been lower, much lower than those of men. And we also find that female scientists in the US earn much less than male scientists in biology, chemistry, and physics. This gender gap has somewhat reduced in the past 20 years, but we still find the gender gap in salary, in funds, is still significant. So we are trying to quantify the phenomenon and find out the reason behind it. We want to know what makes the gender disparity. And if we can understand the mechanism quantitatively or qualitatively, we may help the policymakers to design innovations to help improve the gender balance. So to quantitatively answer the question, we rebuild scientific careers based on the Web of Science data. So you may be familiar with Web of Science. When you search for literature, they granted us full access to all of their metadata for bibliometric analysis. So we were licensed to access a total of 55 million papers from 1900 to 2016, including all the natural and social science journals indexed by Web of Science. And so we knew how those papers were organized in 154 fields, and which will later group into 13 major fields. And we know how those papers cite each other. We know the citation network, and we know their authors. We know their names. We know their affiliations. And based on that, we can rebuild scientific careers trajectory. We know how they move between universities. And so there are a total of 98 million author names on those papers. And we group those names into 7 million individuals. So we queried the author's first name in a public name library from over 100 countries to infer their gender. So, in most languages, your first name gives us hint about your gender, like if your name is Mary, you're female. If your name is Mark, you're male. So with that gender labels, we were able to analyze those authors to explore the relation between gender and their publication and citation reports. The gender inference algorithm is reported 90% or 95% accurate in most of the countries, like in the US, in Europe. And we exclude some countries in which we were not confident about the gender inference, like China, Korea, and Japan. So our analysis did not include and should not be applied to those countries. So we started to establish the phenomenon of gender disparity by checking the population trend. This is the number of actively publishing authors in every year since the beginning of our data, 1900. That is how many male and female scientists published at least one paper in each year. So not surprisingly, both numbers grow rapidly after World War II. In each year, we observe much more male scientists publishing than female scientists. In 1945, when the number started to grow, there are 12% female scientists. And in 2005, the fraction increased to 35%, which is a big improvement. But we still see female scientists are large underrepresented from the past to nowadays. And then we inspect the ratio of male and female scientists in each discipline and each country. So we have identified 8 major disciplines in our data, from math, physics, computer science to poli-sci and the psychology. So in all of the 8 disciplines and in most of the countries we have analyzed, we find much more male scientists than female scientists. We don't report sociology here because the data didn't cover a lot of social science journals. And besides, we find a very interesting phenomenon that the gender disparity is not consistent. So the inequality itself is not equal. In some disciplines and in some countries, like in math, in the United States, in South Africa, we see much more male scientists than female scientists. And in some disciplines and countries like Russia, like Argentina, we see the gender disparity is very small. So what makes the difference? Why the inequality itself is also unequal? This will be our key to explain the gender gap in the scientific careers. So now that we see men outnumber women, so it is unfair to compare all men as a whole and all women as a whole. So therefore, next we focus on the individual level. We want to know, we will compare a single an average man and an average woman, who has a higher performance. When we're talking about scientific performance, we are really talking about evaluation. There are many ways to measure how successful a scientist could be, or how a scientist is recognized by the scientific community, like prizes, like titles, tenure track, H index, impact factor. So here we use two simplest ways: the number of publications and the number of citations. So roughly speaking, a scientist with a greater number of publications and citations are usually more recognized in the scientific community. So here's a random example we selected from our data. So the brown dots represent all the papers published by this author, and we sum up it to get the total number of papers, which is 43. That's his total productivity in his career. And also collect the number of citations of each of those papers, as shown as the vertical line. And we sum up the authors to the author's total impact, which is 1,700 citations. Now, to avoid unfair comparison between old papers and recent papers between disciplines, we only count the number of citations within 5 years after a paper's publication, and we normalize the paper. We normalize the citation numbers by the average citation number of all the papers in the same year in the same discipline. So we hope that helps us to fix the citation inflation nowadays than 100 years ago, and to make citations in different disciplines comparable. And also count the years spanning from the author's first and his last paper as his career length. And here is the total of 11 years from 1994 to 2005. And we also count the average annual productivity. That's the average number of papers per year. So those are the quantities we are mostly interested in measuring how successful a scientist could be. And we count this for every individual and check the difference between genders. So here are the results. Men have shown significant advantage in total productivity. On average, a male scientist publishes more papers in his career than a female scientist. As shown here in the top bar, male scientists on average publish more 27% more papers than a female scientist in the whole career. So this advantage is consistent when we break down all the authors to countries, to disciplines, and to the cohorts, and also to the university rank. This is quite consistent. So we know that for all the countries, all the disciplines in different ranks of university and in different time in the history, we see the consistent advantage that men publish more papers than women. And it's interesting that when we further group male scientists and female scientists by the number of papers and compare top men versus top women, middle men versus middle, and low performing men versus low performing women, we find it's interesting that the gender gap only appears in the top group. So in the top group, the 20% most publishing men, they publish about 37% more papers than women, than the most publishing women. But in the middle and the low performing group, I don't see a significant gender gap between them. So this is a very interesting finding that male and female scientists, their gender gap only appear in the top one, in the senior guys. Similarly, comes the gender gap in total impact, that men have much more citations than women in the whole career. Again, the gender gap is consistent across countries, disciplines, university ranks, and cohorts. So again, we break down people into 3 groups by their number of citations: the top cited men and women, middle ones, and the low cited ones. And we also find the gender gap is only observed among the top guys, among the most cited men and women. And when we are looking at the middle and low performing men and women, I don't see a significant gender gap. And I even see that female scientists, they have slight advantage over male scientists. So that suggests that the gender gap in performance mostly come from the big names, the top scientists. So why? Why does a single male scientist outperform a single female scientist? Why is the gender gap mostly observed in the top group? So we will start by inspecting a stereotype. So there's a widely spread stereotype related to this gender gap, that women are less talented in philosophy and STEM, like science, technology, engineering, and math. In a 2015 science paper, Leslie found that in some disciplines, people believe talent is a key to your scientific success. And in those disciplines, there's a worse gender balance between male and female scientists. So this finding reveals that a lot of people in academia hold the stereotype that women are less talented in STEM. And we examine this stereotype with annual productivity and the citation rate, which is the average number of papers and author published per year, and the average number of citations an author received per paper. So if we see on average a male physicist publishes more papers than a female physicist every year and gets more citations than a female physicist in every paper, we might say that, okay, the stereotype is possibly true that men have more talent than women in physics. Is that? No. The data show no gender difference in the average number of publications per year and in the average number of citations per paper. So on average, a scientist, no matter male or female, they publish 1.3 papers per year. And the gender gap is very small. You can see the figure K. The gender gap is very small. It's even negligible. The men publish 0.9% more papers per year than female. And the citation rate is similar. And we find that female scientists even have a slightly higher citation rate in the average number of citations per paper than male scientists. So when we break down the data into high-performing and low-performing scientists into countries, disciplines, and cohorts, we still observe the same phenomenon, that there's no significant gender gap between men and women in the annual productivity and in the citation rate. So in the fields covered in our data, the stereotype is not true. Women are not less productive and are not less cited than men. So when we consider the union outcome per year and union outcome per paper, that brings the difference so that inspires us to ask, what brings the difference in the career-wise comparison? The answer is obvious, accumulation. So that's why senior guys have a larger gender gap. So men stay much longer than women in academia. On average, a male scientist keeps publishing for 11 years, while a female scientist stays in academia for 9 years on average. So this is ironic that when people stereotype, men are more talented. The fact is, men have no advantage in annual productivity, but instead, men have an advantage in staying longer in academia. So since their only advantage is in career length, we propose the hypothesis: can we claim a causal relation that a gender gap in career length leads to the gender gap in productivity and total impact? So to find the answer, let's recall what we reported earlier, that gender inequality itself is not equal. It is not consistent. In some countries, the gender gap is huge. In some countries, the gender gap is small or negligible. Here are two examples, the Netherlands and Cuba. In Netherlands, men and women differ a lot in career length, and they differ a lot in total productivity. And in Cuba, there's a much smaller gender gap in career length, and there's a correspondingly smaller gender gap in total productivity. And this is not a coincidence. We find that alignment is consistent in almost all the disciplines and all the countries. In some disciplines and countries like biology, just here, and Germany is here, that we find where men have a greater advantage in career length, may also have a greater advantage in total productivity. And in some disciplines and countries like applied physics, physics is here, and Columbia, men and women are almost balanced in career length. They are also almost balanced in total productivity. So this is a very simple linear relation, and it inspires a hypothesis that the gender gap in career length might solely explain a major part of the gender gap in performance. To validate this hypothesis, we use a matching analysis. So we simulate a scenario where there's no gender gap in career length by creating two samples in which each man is paired with a woman with the same career length, the same country, the same discipline. So in practice, we ended up with 400,000 of men and 400,000 women, and they are identically distributed over career length, discipline, and country. If the hypothesis is true, there should be no gender gap or very small gender gap in performance between those two samples. And the result is that the gender gap in performance has been largely reduced in the matched samples. To recall the real world, so recall the real world gender gap. Male scientists have 27 more papers and the 30% more citations. And when we do the matching in this counterfactual world where there's no gender gap in career length, we find that gender gap in performance is reduced from 27% to 8%, from 30% to 12%. So people may argue that the reduced gender gap attributes to controlling discipline because we control career length and discipline and country. So they may argue that this is because we have controlled the discipline rather than we have controlled the career length. This is quite intuitive because we know that men and women are different distributed in disciplines. There are more male scientists in highly productive disciplines like computer science and biology. So we do another matched sample. We construct another pair of samples to inspect this possibility. This time we only control discipline, but not career length. And the result is when we compare men and women in the same discipline, the gender gap is even worse than the real world population. Men have 31% more papers and 38% more citations. So that is to say, it may be true that men and women are different distributed over disciplines, but that difference does not explain the real world gender gap in performance. So the gender gap disparity that female scientists are underrepresented in publications and citations is not a consequence of the unbalanced distribution of disciplines between men and women. Instead, it is largely explained by a single factor that we just examined, the gender gap in career length. So this confirms the importance of career length in gender study. It also falsifies the stereotype that women are less talented. So when women and men, they have equally long careers, the difference in publishing and being recognized is very small. So next, let's ask, why are female scientists have shorter careers? So the answer is dropout rate. In the left panel, we report the expected dropout rate in each year after scientist publishes the first paper. So we define the academic age as the years, as the number of years since your first paper. So, and we calculate the dropout rate as the probability that a scientist will stop publishing in the next year. So we see a consistent trend. The female scientists quit academia at a higher rate in every stage of their career, from graduate student to postdoc to tenure track to tenure professor. So this results in a consistently lower survival rate, as shown in the right panel, that women are less likely than men to stay in academia for 10 years, for 20 years, for 30 years. And can we say the excessive dropout rate causes the gender gap in performance? how do we know the excessive dropout rate is a cause, not a consequence of the gender gap in performance? So in one story, as most people stereotype, the female scientists suffer from excessive dropout rate because they are not performing well than men. So in academia, people say, publish or perish. If you don't publish a lot, if you're not cited a lot, you're out. But that is not the case here. We have compared the dropout rate of male and female scientists by controlling their publications, the cumulative publications and the citations in each year. And we try to predict their dropout rate in the next year. And we still find that after we control their performance, when men and women, they have identical distribution on publication and citations, female scientists still have a higher dropout rate, about 2% more probable than male to quit the academia in the next year. So that's how we claim that excessive dropout rate of male scientists is not because they are performing well. And so we want to check whether the dropout rate is a cause of their performance. Then we won't say that there's an unknown reason that we have not explored. The female scientists suffer from excessive dropout rate, and that leads to that limits their academic performance because they are not staying in academia for enough long. And how to identify the excessive dropout rate is a cause? The answer is we manipulate. This is a very interesting example of causal influence from one of my favorite books, The Book of Why by Julia Pearl. Say we observe a correlation between a storm and a barometer. So when we observe a storm, we see the barometer shows a lower air pressure. How do we know it's the storm that triggers the barometer or the barometer triggers the storm? The way is to manipulate. It is not easy to manipulate the weather, but it's quite easy to manipulate the barometer. So if we manually change the barometer's reading and then a storm comes, we will know the barometer is the cause of a storm. But if we manually change the barometer's reading and the storm does not come, we will know the barometer is not the cause of a storm, and it's probably the storm is the cause of the barometer. That's what we're going to do. We manipulate the gender gap in dropout rate in our data, and we see whether the gender gap in performance will be changed. So specifically, we manipulate to increase the male scientist dropout rate, such that men and women have identical dropout rate when they are at the same academic age with the same performance. In practice, each year we count how many male scientists will drop out in the next year. For example, 2 years. So in 2001, there are 6 male scientists. In 2002, there are 4 remaining. So we know 2 male scientists quit academia in 2002. And also count how many female scientists quit. Here we have 3 female scientists quit in 2002. And to manipulate the male dropout rate, we require 3 men to quit. So we randomly choose an unlucky man and we force him to quit. So in our data, we pretend he quits academia this year, and we delete all his publications and citations after this year. Then we recalculate all his publications and citations. So we will update his number of publications from 43 to 37, and we remove all the citations of his later publications, and we recalculate his number of publications and update from 1700 to 1400. So in this counterfactual setting, we see the gender gap in total publication and citations have been largely reduced from 27% to 9%, from 30% to 12%. And we believe this is quite convincing. But we'll also do various versions of the counterfactual analysis by controlling different factors, including the number of publications and the citations, the countries, disciplines. We try to control all the factors we can imagine about, and we got similar results. So this analysis supports our hypothesis that excessive dropout rate of female scientists is a cause, not a consequence of their underrepresented performance in academia. So this is our final conclusion. It is a pity that we could not go one more step to figure out why female scientists quit at a higher dropout rate. This was limited by the data. There were a lot of hypotheses trying to explain why female scientists they have a higher dropout rate, like their family support, like they have more obligations in raising kids. But our data, we have nothing in our data to reflect those indicators. So that's why that limit us to move on one more step. Similarly, we do another counterfactual analysis, shows that when there's no gender gap in the publications, there will be no gender gap in the total impact. Actually, male and female scientists, they have the same citation rate when we control the disciplines. So to summarize, we quantify the gender gap in academia, in which female scientists are outnumbered with less publications and less citations. The gender gap is observed consistently across disciplines, countries, institutes, and cohorts. And we find two invariants related to this gender gap. Male and female scientists, they publish the same number of papers per year, and they get the same number of citations per paper. This is true across disciplines after we adjust and normalize the number of papers, number of citations. And we point out that female scientists' excessive dropout rate can explain a major part of the gender gap in performance. So we first find the correlation, and then we suggest the causal relation that females' excessive dropout rate is probably a cause, not a consequence, of the gender gap in performance. And this excessive risk lies in all the stages of a female scientist's career, from the very beginning to the very late stage. And so our final claim is that if we can provide a fair environment for female scientists in which both male and female scientists are rewarded an equal chance to stay in academia when they have equal contribution, when they have equal number of publications and citations, we will see that female scientists will achieve almost the same performance, the same scientific success with men. Thank you for coming to the talk, and thank again to my collaborators, Alex, Roberta, and Laszlo. Questions? Yes.
So you're looking at this data over the years, right? And so you're looking at the data over the years, and you're like, depending on the data, you are trying to see if there are more male citations versus female, like citations from or like papers published from like female authors. What is the possibility that some of these authors were actually writing in pseudonyms? Because some of the cases where the early cases of like 1900, there were many female authors who were like not credited enough, but they were actually behind some of those publications at that time, right? So could it be the case that some of these publications that are credited to male authors were actually, on the behind the scenes, like work by female authors? Is that something that can be investigated with this data?
So I didn't quite clear listen.
Yeah. So what I was saying is that are we miscrediting female authors versus like male authors in some of the older publications? Then is that something that we can get from the data set?
So you mean in early years, female scientists were
close to like 1900s, 1920s, because you're looking from that years, right? Like from 1900 all the way to present day.
In early years, female scientists were identified as male scientists. Is that what you're saying?
That or either they were like working behind the scenes, and then the publications actually quoted only the male authors and not the female authors. So,
oh, you mean male scientists were not recognized?
Yeah, no. So like, let's go with the invention, like the discovery of DNA, right? So there were, people often credit Watson and Crick,
but there was a female author who was also a part of it, but she was not often like, said. So there are many cases like that in the earlier. And is that something that we can actually?
Oh, so
data?
okay, I'm not sure if I got your idea. So you're worried about in early years, some female scientists, they have contribution, they have scientific contribution, but they were not named as a co-author.
They were not named.
It is possible.
And is that something you can actually find from the data? If it's not possible, then yeah, this is not the data.
Yeah, it is possible, especially in the early years, because we have very, very sparse data in early years in 1900. So actually, we have very few data before the World War II. And it is possible, but those data are okay. So some female scientists were not named in early years. It is, I think it is possible, and even not in early years, but in 1960s, 1970s, there's still the phenomenon that a lot of female scientists that publish without their first name. So I know it was reported that female scientists in 1960s, 1970s, they prefer to publish journals in which the authors, the author full name were not shown. Say Hongbo Fang will be shown as H. Fang, not Hongbo Fang. So because they believe their name when they submit a paper as Mary, they might be so the reviewer might discriminate them. That's what their concern. So we also encounter this problem that when we identify female names in early journals, early papers, a lot of author names were just initial instead of full name. But luckily, we were able to merge Web of Science and Microsoft Academia Graph, and for unknown reason, Microsoft indexed their full name. I don't know why, but so we try to link the two data sets, and whenever we find an author misses his full name in Web of Science, we link the name. In Microsoft, and that's how we got their full name and infer their gender. Back to your question, I think it is true in early years that some female scientists were not recognized, and that could contribute to what we have found that female scientists, they have a lower number of publications because they are not named. But we believe that is not a major cause because so first it was a very, very early years, and in those years the number of publications were very few. In Albert Einstein stage, the total number of papers per year in the whole world is like hundreds. And nowadays I don't have the data, but I personally believe it is not that bad in like 100 years ago. So in the majority of the statics in our data, I guess this is not a major cause. I think the major cause, as we just showed, is the career length. Then female scientists, they are not rewarded the same chance to stay in academia enough long, so they are comparable or competitive with the male cohorts. Thank you. Yes.
I have two questions. One is an extension of this question, and the other is a separate question. The extension of this question is that I can confirm that that in the 70s and even the 80s, women were advised to publish under initials. I ignored that advice, but I got that advice.
Yes.
But there must be some cases in which you could not identify the gender of the author because some names are simply ambiguous. Was that a significant fraction of the data? Because if it was a significant fraction, then that leads to the question whether there's a gender imbalance within that unknown segment. But if you were able to identify the gender of most of the authors, then it's probably in the noise. So I mean, you excluded countries from which names are frequently ambiguous. But in the countries that you did study, there are still names that are gender ambiguous, like Sean and Alex. And I had a roommate once named Marion, spelled the male way. Was that a significant fraction of the data, or is it inconsequential?
Good question. So when we infer the gender labels of all the authors, we do find some labels were inferred with low confidence, and we exclude them. So as I just mentioned in the data process, now we query our author names in the public name library, and they will return us with a gender guess and the confidence. And we exclude all the names without a high confidence. I think we removed all the names with a confidence lower than 70% or 90%. And
Was that a large number or a small number?
it's a small number.
Okay, then it probably doesn't affect the results.
I believe so.
Okay,
So
then my second question is about the graph with the dropout rates. The curve, that one. The striking thing here, so you're measuring academic age from first publication, not from PhD. It's often measured from PhD, but for this data, first publication makes sense. Many students publish before getting a PhD, and so I assume that initial spike in both genders reflects students who published as PhD students, but then went on into jobs that
That's
didn't
true.
involve publishing.
Yes.
I'm interested in your interpretation of the next segment, in which the women drop out at higher rates for about the next 4 or 5 years. Do you have any interpretation of that, or do you have any ideas about how to investigate that? Because if you take that particular gap out, then the orange curve drops down to look a whole lot like the blue curve.
So even there's no gender gap here, we still find gender gap in the
Right,
whole
but
career.
if you take that curve and if you eliminate that steep segment in years 3 to 5, 3 to 8
Yes.
for the women, if you eliminate that dropout rate, doesn't that, no, wait, these are percentages,
No, this is not cumulative dropout.
right? Sorry, those are rates.
Yeah,
But-
but I
But do
do.
you have any explanation? Do you have any way to investigate that very high peak at the 8 to 10 year mark?
I do agree with you that there's a high peak here in the very early stage of the career, and I believe that relates to when they graduate. So when a PhD student graduate, a lot of them they quit academia, they go to industry, and so that's why we see a peak in both male and female scientists. And why there's an even higher peak of women than men, we didn't have the data to examine this, but we have some guess that because this is like 5 or 7 years after the first publication, and most people at this time they were like in their 30s and they have their first kid. So the female scientists are expected to spend more time with family support, and that gives them a higher pressure, and so they have less time to spend on their research, and that limits their performance, which perhaps makes them more fragile or more vulnerable to quit academia. We will think about this, but we failed to find data because what we have is the bibliometric data. We know how to publish, how they are cited, but we don't know when they got PhD student, when they got PhD degree, when they got married, when they got first kid. We didn't know this. So that's why we didn't explore, but I want to introduce, bring your attention to this paper. This is, I think it's ongoing work. Last year, I met in a DC conference. This is by a sociologist, Chao-Chun Yi. Okay, so she analyzes the gender gap in the dropout rate in the achievement, and she relates their performance with the work-family conflict. And she found a very interesting phenomenon that when you split women scientists into 2 groups, with kid and without kid, and she found that female scientists without kid, they perform almost identical with male scientists. So that's why she concluded that the family support brings a pressure to female scientists, and that might be the major cause of their excessive dropout rate.
That certainly makes an interesting suggestion about university policy about assistance with family care, doesn't it?
Yes. It is. Yes.
Yeah, just out of curiosity, I wonder if male scientists start their career earlier than female scientists.
Start earlier, you mean age?
Yeah, like they publish earlier than their female counterpart.
We don't know. We don't know their natural age. We only know when they publish their first paper.
Mm.
But might be true because if you check, maybe it's inverse because you see the male's peak comes earlier than female's peak, and we guess that peak is when they graduate.
Yeah, I have a question about after you control the dropout rate and made them to like the manipulate the data to have the male have the same dropout rate as a female, then there is still like 9% to 12% of difference between the female and the male.
Yes.
So I want to know if there's what's the main reason between the change after we control the dropout.
You mean why they are still
Yeah.
gender gap?
Yeah.
We don't know. This is some. So what we want to show is that once we control dropout rate, we have control a large part of the gender gap, but there's still a small part that we fail to control, and we didn't find an answer in our data. So there might be, so the answer might be somewhere outside our data. So as I just mentioned, that we have a lot of data limit that we don't know their marriage, we don't know their family, and we don't know they got tenure track. We have a lot of misinformation, and I guess the answer is in those misinformation.
Yeah, I see.
Yes.
I have a follow-up question on these counterfactual experiments. How do you randomly drop the male students? Do you like drop them uniformly at random?
Yes, yes, that's why we call randomly.
Is it possible that the people who drop out are the students who are performing the worst? So by dropping out uniformly at random, you're potentially dropping out male students that could be performing well.
I mean to simulate publish or perish.
Oh yeah.
Okay, so so this is one version of our counterfactual experiment that we randomly select the male scientists dropout rate to drop out, and we also have other versions that we drop out by their publications, by their citations. So here we group people by the year and by their age. So we have, say for example, we have all the scientists here. They are in their 10th year when it's 2001, and the next year will be the 11th year. And we randomly drop out one male scientist. And we also could group them by their age and publication and citation. So here are people with in 2001 with like 10 papers, 100 citations, and at the same academic age. And we believe those guys are kind of identical in our data. So we still randomly drop out a male scientist, and we check the result, and the result is quite similar. So we believe the way we choose someone to drop out is will not significantly change the final result.
So basically in all these different settings, you observe like a similar result.
Yes, similar result. And so we didn't try the idea to drop out the least performing male scientists, because female scientists were not drop out in that way. Female scientists were not ranked by the papers, and you drop out the lowest performing one. This is not female scientists. So all the female scientists, whether high performing or low performing, they all always have a a rate, a possibility to drop out, and that occurs too many.
Right, but the problem is if you drop out this, like the students with who publish like highly influential papers, then in later years their papers are not getting cited. So it might, because the dropouts are like correlated in time. So I'm still wondering if there's a fact where you just drop out students randomly, because it sounds like you're not. It sounds like it might be necessary to consider this kind of time correlation.
Yeah, I think as I just mentioned, I think another version of our experiment has already answered the question, because when we group them by their publications, and in different groups of publications, they have a lot of larger different dropout rates. And in the low performing groups, people have a higher dropout rate. And so I think that helps to answer your question. The low performing guys are more probable to be chosen to drop out. And we also, sorry, let me finish his question. And we also have an observation, which was not included in today's talk, that we know that the dropout rate is correlated with the number of publications. And we know that female scientists, they have a consistently higher dropout rate when we consider their publication. So it doesn't matter you are low performing or you are high performing. Female scientists still have, I think it's 2% or 5% higher probability to drop out from academia than male scientists. So I think that helps to answer the question and why we choose to randomly select them, because it doesn't matter we choose them by age or by publication or by citation. When we control their age, their publication, their citation, it is fun to drop out to select them to drop out randomly. And I think your concern has already been encoded in the way we group them.
Thank you.
Yes.
So this answers half of the question I was going to ask, which builds on his question. Have you looked at the female or male? Have you looked at the dropout rates and year to year to see whether the scientists dropping out are the low performing scientists? I think your data would support that question. And if the answer is that the dropouts are more likely to be the lower performers in their previous career, then I'm back to his question, which is if you're going to do a dropout, why don't you drop out where your distribution is similar to the dropout rate that you observe against the question, are you more likely to drop out if you're a lower performer?
Yes, it is true. Yes. So if you have a lower number of publications, you have a higher dropout rate.
Okay.
It seems like I also come in late, so it might be a piece of information that's left out. But it seems like a huge measurement for like successful, and then like academic success seems to be this number of publications. But I feel like, at least for me, like in system architecture, like our publication number is significantly different compared to people who are in ML. How is that factored in terms of like numbers of publication expectations different for different areas and stuff?
You mean how this is related to the gender gap?
Related to what?
To the gender gap?
No, I was just wondering, like, because it's not related to gender gap, but I feel like you can't equate saying someone publishing like 4 papers in system, which is like top papers in system, which is like already super performing compared to someone who published for like ML paper and the top conferences. Like number of publications, not only the measurement of success rate. And then if that's the only indicator of like how performant this like engineer scientist is, like is that too simple of a model?
Good question. So you're asking the number of publications have different meanings in different disciplines. That's why we control discipline when we do the comparison. So when we are comparing male scientists and female scientists, we compare physicists with physicists, we compare sociologists with sociologists. I don't think we have a lot of comparison across the discipline. I mean, we don't compare male scientists, male physicists with female sociologists because that's a fair comparison.
But she's asking about the differences within computer science.
Within computer science, we didn't do that. So as I just mentioned, that we have a total of 154 disciplines, but we group them into 13 major disciplines. We didn't want to break them down into very specific topics because that would make our data very sparse to analysis.
This might be stupid, but I just thought about it on top of my head. Like, I think looking at different areas is definitely one way to do it, but like in terms of this huge discrepancy, like inside of CS, which is like a growing, expanding field, would it be easier if we just take samples of the top performant scientists in each area? Like we don't even group them in an area, we just kind of count their papers and use that sort of as a measurement, and using that paper count for the top, like group people by what's considered as like the top performant publication count instead of grouping them based on specific area of what they're working on, if that makes sense.
Yeah, I should understand. Very good suggestion. So to differently consider people in different specific topics and to find the topic or subfield specific bars to evaluate, to define the high performing level of people.
Yeah, and maybe even just get rid of the subfield, also just using that bar.
Thank you for the suggestion.
Oh,
Any more questions?
Well, I think at the start you showed some trends over time, right? The gender gap is narrowing a little bit.
Yes.
Yeah. Were there any specific points in time that were notable, or is it just like as this shows this like continuous trend, or are there like clear changes in the way academics works that cause gender gap to reduce over time?
So are we doing better now than 60 years ago? Is that what you're
No, I mean, this is kind of clear, right? That's the case. But I mean, what would you attribute to? Why is it improved? Or is there any ideas as to why it's gotten a little bit better?
So I didn't quite catch your question. Can you?
Did you try and correlate or like draw any conclusions from points in time where the ratio changes significantly with changes in academic methods of publishing or anything like peer review being anonymous?
Yeah, that's a good question. So I believe there are a lot of interventions in the past couple of decades that help female scientists to get a more fair environment, to get more fair treating in publishing, in peer review. And I think that was one of the causes that we see a smaller gender gap now than 60 years ago. As I mentioned, that we have a lot of limits in our data. We don't know that we don't have data to evaluate the information that you just suggested, like the peer review, like the journal preference. But what I do know some journal study that mentioned this question. I remember one paper that mentioned that in they check some journals, some top journals, and they divided those journals into stages when the journal changed their chief editor. So they realized that when a journal assigns a female scientist as the chief editor, the journal becomes a little bit more gender balanced. more female female author papers on that in that journal. And I hope that can reflect something in the peer review, that when female scientists they are in charge of the editors, that might change their way of like selecting editors, selecting peer reviewers, and that could finally influence the peer review process, that could be makes it more friendly to female authors. Yes.
One more. This is about the use of publication counts as a proxy for quality. At the outset, you used Nobel Prizes as a way of showing correlation between publication rates and some other measure of quality or significance or prominence. And then later you talked about causality and what you can manipulate. Publication counts are widely suspect as a driver. They're regarded more as a consequence. Do you have any other data that would support the use of publication counts as a proxy for quality beyond what you said about Nobel Prizes?
Good question. So I guess
It's the elephant in the room. I had to ask.
yeah, thank you. Unfortunately, we don't have price information or tenure information in our data, but I believe we can check this by checking their price, their funds, their tenure years, and related to the number of publications. Of course, we need to control the discipline. And so I guess a higher number of publications and citations are correlated with price, with tenure position, or even with their funds. We don't have data, so
Here's an idea. The professional societies give awards of various sizes.
yes.
You know, there are the fellows, which are quite numerous. There are the individual prizes per year. Many of the publication venues that you're investigating are associated with professional societies that have prize lists. So I think there's a source of data there that would present an opportunity for you to investigate the relationship between publication counts and other measures of success and quality, such as professional prizes. So
Yeah.
I'll offer that to you as a line of investigation.
Thank you. This is I should read this as very yeah, I think it's totally doable, as you just mentioned, that we can crawl the award list or the funds information and try to relate that to the number of publications and citations, and see whether the number of publications and citations actually reflect how successful a scientist could be. Yes.
More question? No, let's thank Jimmy again.